Now, how does this additional term impact the linear system we end up solving? All right, so let's continue with our derivation of finite element, but carrying this additional term. In finite elements, we started with the weak form, right? We have the weak form in the integration from 0 to 1, dv, dx, du, dx equal to integration v times f. And again, if you look at v being a linear combination of different vi's, in order to enforce the weak form for all the vi's that satisfies such formula, we only need to enforce this weak form for v equal to vi when I is equal to 1, 2, 3 up to n minus 1. So there is n minus 1 vi's, there is n minus 1 v's, there is n minus 1 linearly independent v's we need to use to enforce this weak form. Okay, so if we plug in these n minus 1 linearly independent v's, and we also plug in the green formula into du dx here, what we get is integration from 0 to 1. The v's are going to be replaced with vi for n minus 1 different i's. Okay, these are all the linearly independent v's out there. Times d dx of a summation uj. So let's use j as the summation index over here for the values of u. Okay, dx would be equal to the integration of vi f dx. Now, this is what we have last time, but this time we added one additional term, right? And that's going to be added over here. That's going to be added in the formula of u. So there is one additional term plus a times vn. All right. And in the last lecture, we have converted the entire left-hand side into a matrix and the entire right-hand side into a vector. But we're going to see that the additional green term here is going to make the left-hand side to be something a little bit more than just a matrix. So let's go to the next page. Okay, so following what we have written down on the last page, what we had is this integral. But first of all, let's actually expand this summation, the sigma summation and this summation. Because of the linearity of the derivative, we can move the summation out of the derivative, and because of the linearity of the integral, we can move the summation out of the integral. So we'll have a red term and a green term, and we are already moving them outside the integral. So the red term becomes a summation of j goes from 1 to n minus 1. The coefficient is uj, okay? And inside we have the derivative of vi times the derivative of vj dx. All right, then we have this additional term we had because of the boundary condition, and that is a times integration 0 to 1. We still have the same dvi dx, but here we have a new term, dvn dx. So this is, the red term is exactly the same as before, and the green term is new. The right side is also the same as before. We have vif dx. Okay. we have denoted this integral as aij and discussed how do we compute that, right? So this new green term actually has really no difference from this aij over here. So we'll just call them ain when n is actually beyond the summation index for j inside the matrix. All right. Okay. So maybe here, let's don't confuse between this small a, which is my boundary condition, with the aij, which I use to denote my matrix entries. So maybe I should use a big A here to denote that this is actually an entry in our matrix instead of the boundary condition. Okay, we have also used the bi to denote the integral on the right-hand side. So instead of a linear system a times u, where u is the collection of all the unknowns from u1 to un minus 1, instead of au equal to b, right, where b is our collection of right-hand sides, we have au plus something, right, equal to b. And this something is my right boundary condition times a, let me write it as a dot n. A dot n is actually, it almost looks like an extra column in this matrix, right? It's a column vector, but the form of it, how do we compute it, is actually pretty much like just an additional column in the matrix. All right, so this is how our new linear system is going to look like, and it seems basically a small addition to what we have already done. Okay, so before we go to MATLAB and try to add this addition into our solver to see how it works, do you have questions on how the derivation went through with this additional boundary condition?